Hey there, I'm Max Doolin, and this is the Spokane Cyber Cup Year 6 Challenge Bad Keys. If you went to the event last year, we actually had a challenge very similar to this. This challenge is about a bad seed, and the other one was also about a bad seed. But the ability to get said bad seed and how why the seed is bad are entirely separate. Last year, it was because it was a very small number. It was only 2 to the 20 power, which is brute forcible. This year, it has to do with something else. So let's read the prompt. My friend Joe Grant has a crypto wallet, but cannot remember the key that it generated. They lost their wallet. And in crypto land, if you lose your private key, you're totally screwed. There's no way to get it back, for the most part. Or if you have a hardware wallet and you forgot your PIN for it. So he says, can you help him get it back? His public key is this. He said he generated the key on November 1st, 2024, if that helps at all. Read the Python code that was used to generate the private key. From there, find the flaw in the generation and exploit it to find the private key. The flag for the challenge is the hex encoded private key. Hints. For some inspiration, this video helps. And this video is actually a video of Joe Grant using this exact tack in a older crypto wallet to recover the private key and get the funds, which is kind of cool. So it says hints, work smarter, not harder, reuse the code for generation in order to find the key. So if you look at the key generation here, it's pretty small. The generate key function is here, and we call that in a second, a little bit further down. We're then getting the date time and converting that to the timestamp and taking the integer of it. This is the Unix timestamp, which is the amount of seconds since January 1st, 1970. We are then printing the seed, and then we are using the seed to generate a key. In order to generate a Bitcoin private key, it needs some sort of randomness, and it makes you choose what your randomness is. So when we call from entropy with our bytes seed, we are specifying the bytes that should be used for the randomness of this. After that, it prints out our key and prints out the nice address that we get to use. So what's the big deal here? What's wrong? And like before with the previous challenge we had last year with the bad amount of entropy, it's the same thing. The big thing to notice is that it says that the key was generated on November 1st of 2024. If we look here, we can see that it's using the timestamp in order to generate the seed. Well, if it was generated on November 1st, 2024, that means that this isn't really random. We can know what that seed was. And this is going to use a concept called brute force. We don't know what second or what Unix timestamp it was, but 60 times 60 times 24, 60 times 60 times 24, isn't that big of a number. I mean, 86,000, that's something you could reasonably brute force on your local computer if you wanted. So, what is the timestamp for this? Here's a website. I literally just went to Google, did timestamp today, and then you can go to it. And right now this has other dates, but we can actually change this to get this information. Cool, now we do convert, and it gives us the actual Unix timestamp for this. So we know that this is the actual time. This is the first part of the timestamp. This is the first part of the seed. And this could be within a 24-hour period, so we're going to have to try all of them. In the challenge, it says to work harder, not smarter. Smarter, not harder. And so we're going to reuse the code here. And luckily, it's not too bad. The students will need to figure out how to install this BIP 32 utils. I'm probably going to add like a pip install thing just to make life easy for students, because Python dependencies can be annoying if you've never dealt with it before. So we have the script that generates it. But the thing is, we have a new seed that we want to try. So this is going to be our starting seed here. So seed equals that. And we're going to do gen key, or just do POC. Cool. So at this point, we could try and see if this generates the right thing. And we'd want to see the address be this address. So this is what we want to see. We'll notice that 1N and 1.5 are different. So now we can, oh whoops, that is the wrong program. Cool. Well, we'll notice that these are different. So now we can do 1. We can go up 1 more. Now the key is different, but it's still incorrect. So the idea behind this is we're going to try every single key for a 24-hour period until we get the right one. So this is the perfect situation for a little for loop. We know what the starting seed is. We can do for I in range 60 times 60 times 24. It's because we have 60 seconds, 60 minutes, 24 hours. We need to generate the new seed that we want. So we're going to do seed plus 1. And now that will generate the proper one. And then we need to determine if this entry is correct. We could determine if the entry is correct by comparing the key.address to the key, or this is the public, or the address. So in Bitcoin, you have a public key and a private key. This is because it uses asymmetric cryptography. And I believe under the hood it actually uses elliptic curve digital signatures. But we don't want to do that or use those long values. And so I believe this is just a hash of the public key that was taken, is what it uses as the address. And that's pretty common in most of the blockchain ecosystem, like Ethereum as well. Cool. So we want to compare this string with address here. And if that's the case, then we know we have the proper value, and we can just break out of this loop. This may take a minute because we don't know what the actual value is. But luckily, this isn't some gargantuan number that we've never seen before. And so we can let it run as this goes. So to recap, we know the seed, where we can start from. And we know that there's only so many seeds that this possibly could be. So we're going to try every possibility for that little window where this key was generated. And eventually, we should do the comparison. We should generate the proper key. Because we generate the proper key, we can then know what the private key is. So if we look here, and we printed the address, and this address matches this address, which means that we have the proper key. In the original file here, we have private key.hex in order to format the key correctly. I heard some complaints last year about the challenge not being hard, but for how to format being hard, and so I just added it to the code just to make life easier. So the flag ends up being this hex blob here. And if we look at the solution, it has effectively the same script that I wrote, but this is the flag. And this is a different representation of the key. I can't remember what base that's in, but it's like base 58 or something like that. Yeah, so that's the challenge. I think this is a really fun one. I love having challenges that are things that actually happen in the real world, especially when they have crazy financial impact like these sorts of Bitcoin wallets do. Yeah, so thanks for watching this. I hope this made sense. Thanks.